Hey y'all, it's your math teacher, Mr. Boyden. I'm back at it again today, and today we're going to move into lesson 2, and we're going to talk about arithmetic, sequence, and series. That word arithmetic, it is spelled exactly the same as arithmetic. Arithmetic is the noun, arithmetic is the adjective, okay? So it's describing a certain type of sequence. So let's see quickly what that is. All an arithmetic sequence is if you have a sequence of numbers with some common difference, and we call that common difference D. And IB will also call it D. That's the commonly chosen variable for it. And so when we say that it has a common difference, what we mean is that the pattern is going to be addition or subtraction. It's going up by the same amount every time. So for example, we may have something like 1, 2, 3, 4, 5, 6, 7, 8. What is the common difference? Okay, it's going up by 1, so the common difference is 1. Okay, it's as easy as that. Let's look at another one. 50, 60, 70, 80, 90. What's the common difference on that one? It's going up by 10 each time. So the common difference is 10. Okay, let's look at the next one. A sub n equals 3n plus 2. All right, people, now here's what I'd like you to notice about this one. Do you see how this is of the exact same form as y equals mx plus b, like we had back in algebra class? Okay, so in algebra class, we probably would have written this exact one as y equals 3x plus 2. And then you say, hey, look at that. 3 is the slope, 2 is the y-intercept. Okay, this is very similar to that. The difference is n starts at 1 and counts up by whole numbers, versus in a function like this, x could be any input, any real number, okay? So what are the first 3 terms of this one? Okay, let's take a look. Maybe it's 2. You know, that was the starting point when we graphed them in algebra class. First 3 terms of this one, plug in a 1 here, you get 3 times 1, it's 3, plus 2 gives you 5. Now, since we've already said that this is arithmetic, and we know that the common difference right here, D is 3, it's going up by 3, all I have to do is add 3, so it's going to be 5, 8, 11. Okay, now this connects to what I said in the last video, where we said anytime you see multiplication like that, because multiplication is the same as repeated addition, we're going to see a pattern of addition in our sequence. Okay, let's have a little story. In Germany, in approximately 1785, give or take a few years, there was a young boy named Karl Gauss. And Karl Gauss was probably like 6 or 7 years old, very young, and he was in his class at school. And he was easily the quickest student in the class, so quick that a lot of times he would beat the teacher to answers, and the teacher didn't really like that. So what the teacher did is said, hey, Karl, we have a special little project for you to work on. We're going to get you over here on the side working on that, and it's going to take you a long time. And what the teacher came up with, she said, Karl, I want you to do 1 plus 2 plus 3, and I want you to keep adding up all of the counting numbers all the way up to 100. And Karl, I'd like to know what that is. So go ahead and add those up, Karl, and let me know when you're done. Now the teacher assumed that Karl was going to go back to his seat and literally say like 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, and add them all up, and that would take him, 20, 30 minutes, and during that time the teacher would be able to peacefully teach the class without being interrupted. However, Karl paused, thought for a moment, and then said the answer right back to the teacher. Now, I don't know if the teacher knew the right answer or not. I suspect the teacher was just trying to get rid of Karl for a minute. But sure enough, Karl had the correct answer. So here's my prompt for you. I want you to pause the video, and I want you to see if you can answer this question. What is the sum of all the integers from 1 to 100? Now, it may take a few minutes, and as soon as you hit play, the answer is going to be right up here. Here's how Karl did it. Karl realized that he could start pairing up the numbers. So he could pair up 1 and 100, and that would add up to 101. And there's a 99 in here, of course. And he could pair up 2 and 99, and 2 and 99 also adds to 101. He could pair up 3 and 98, and that would also add up to 101. So what Karl realizes is there are all these pairs of numbers that add up to 101. Well, there's 100 numbers in the list, so how many pairs are there? Well, there'd be half as many pairs, so that would be 50. And so Karl realizes, hey, this problem is as simple as 101 times 50, and that's 5,050. And that's what he shouted right back at his teacher, and the teacher could not believe it. Now, this technique that Karl used is very clever, and it's very cool, but it's a little more useful than that, because this will truly work for any arithmetic sequence if you want to add up the terms. Because there's nothing special about this going to 100. If it went to 200, you could use the same logic. If it went to 500, you could use the same logic. If it was just the even numbers, 2 plus 4 plus 6 plus 8 plus all the way up to 100, you could still apply the same logic. You could pair the biggest and the smallest, and you could pair the next two, and you just realize that instead of there being 50 pairs, that this sequence would only have 25 pairs because half the numbers are missing, okay? So what that comes down to then is a nifty little formula, okay? And so you probably want to go ahead and get this down in your notes. Okay, and this is actually some currency that has Gauss's face on it from when he was a little more old and Santa Clausian. So here's how we break this down. Okay, this right here, this is the first term, a sub 1. Okay, and so all we're saying is we're going to take the first number in the list. This right here says technically it says nth term, but functionally for us what it's going to mean is the last term in the list. Okay, so first term and last term, we are going to add them together. That's exactly what Gauss did, right? Okay, add those together, and then we're going to multiply it by n over 2. What is n? N is simply how many terms are there, or how many numbers in your list. Okay, and we divide that by 2. Why do we divide that by 2? Okay, look at this number 50 right here. We know from 1 to 100 there were 100 numbers in that list, but as soon as we paired them up, there were only half as many pairs as there were numbers. So that's what we're doing. We're taking the total number of numbers divided by 2 because that's the number of pairs they are. How big will each pair be? Each pair will be as big as the first term plus the last. So this now will be applicable to any arithmetic series. Series meaning we're going to add up the terms, okay? So let's look at an example. Okay, and I'm introducing a new vocabulary word here, a partial sum. And all it means is that we're going to add up not all of the numbers in the list, but we're going to add up a certain number of numbers in the list. So this one, if you look at this sequence, it appears to be infinite, ... on the end, right? So we're only going to add up, if it says 50th partial sum, it means please add up the first 50 numbers in the list. Okay, so I want to refer back to that little formula that Gauss gave us. So n over 2 times a sub 1 plus a sub n. Okay, now what they just told us right here when they said 50, they said, hey, that's n, just so you know. So what we are going to have is we're going to have 50 over 2. First term, that's 7, plus the last term, well, that's the 50th term. I don't know what the 50th term is. So we're going to have to do just a little bit of side work and figure out what that is. Okay, so what do we know? We're going to have to write down a function rule for this. So what do I know about that? I know that the nth term of that sequence, let's see, looks like it has a common difference of 11. So it's going to be 11n plus or minus something. So here's how I'm going to think about it. If n is 1, and I plug in a 1 right here, I get 11. And if n is 2, and I plug in a 2 right here for n, I get 22. Okay, I got the pattern right, but the numbers are not right. This says 11 and 22. I want 7 and 18. So all I need to do is minus 4, minus 4. Guess what? I need the same thing on the rule. So I've got my rule, and I need to know the 50th term in the list. So all I'm going to do then, I'm going to find a sub 50, and that would be 11 times 50 minus 4. So what do I get when I do that? So 50 times 11 minus 4, I get 546. And that's my 50th term. All right, now that we know the 50th term, all we have to do is plug it in up here. So 546. And now we're going to simplify this out. So to me, what I see here, I see 50 divided by 2 is 25, and 7 plus 546 is 553. And I think I'll use a calculator for this one. And what do I get? 13,825. All right, so I hope you can see how this formula is useful in the sense that rather than having to add all these up, which would take us a very, very long time, it's kind of a nifty little shortcut. Yes, sometimes you're going to have to do an extra step, but that's something that we practiced in lesson 1, so we already have that skill, and it shouldn't be too difficult at this stage. All right, let's look at another example, something a little bit more applicable. This is not the exact numbers from my home, but this is inspired by a project that I'm going to be working on at home. Okay, new homeowner's making a patio in her backyard with square paving stones. The patio is roughly going to be the shape of a triangle. Row 1 is going to have 50 tiles. Okay, I'm going to write this down. We're going to have 50 tiles. The next will have 48, then 46, 46, then 44, and so on until there is a row that has 0 tiles. So I'm not going to actually put in a 0 here because adding 0 doesn't do anything. I'm going to go all the way down to 2. Okay. How many tiles does the homeowner need to buy? Okay, well, we need to buy what you get when you add all those up. So this would be a really good chance, now that we've already had an example, you can pause the video and you can try this one on your own. Then when you hit play, you'll get some feedback on how you're doing. So maybe pause it now and try this. Okay. For me to find the sum, I'm going to take the total number of numbers in the list. Let's think about that for a minute. It goes from 2 to 50, so it's not 50. Really, it's just the even numbers from 1 to 50, so half as many. So 25 numbers in the list. Okay. First number is 50. Last number is 2. And we're going to divide by 2, and so that should be our setup. So 25 times 52, divide by 2, and I get that I need to buy 650 tiles. Now that we know how to add up all the terms of an arithmetic sequence, let's formalize the name of it, okay? And that new vocabulary term is going to be a series. So series sounds very similar to sequence. Sequence means it's just a list of numbers. Series, it's the same list of numbers, but the only difference is we are going to sum them up, meaning we're going to add them up, okay? I think that's why they use a word with an S, series, for sum. The other thing, people get really frustrated when they see this notation right here, okay? And there's really no reason to be frustrated by it. Right here you can see first term plus second term plus third term plus, we're going to add up all the terms, okay? So that lines up with what we've been doing. We're going to add up all the numbers in a list. This over here, people get a little freaked out. Now the thing that's weird about this is, really, the way math was designed, the people who designed it intended for it to be as easy as possible and for it to be as intuitive as possible. But sometimes we don't think that. So a lot of people think this is the letter E. It's not. And if you think it's a letter E, then yes, this is going to be more confusing. But actually, this is an uppercase Greek letter, sigma. And so what I mean when I say they tried to make it easy, they thought, oh, series, sum, the natural letter to pick would be the Greek letter for an S, so sigma. Now, since we don't learn Greek, sometimes we go, but that doesn't look like an S. No, it doesn't look like an S, but if you're Greek, it does though, okay? So here's all this says. It says we're going to add up all the terms. That's all the sigma means. We're going to be doing some addition. What are we going to be adding up? We're going to be adding up stuff. And we're going to start with the first one, and we're going to end with the nth one. Okay, now that's a little tricky, so let's look at a functional example, okay? Let's look down here. Down here, this says we're going to be adding up all the things of the form 2 times I, and I is going to start at 1, and we're going to stop when it gets to 5. So what we do then is we plug in a 1, 2 times 1, and you can see that right here. And then we plug in a 2, and you can see that right here. And plug in a 3, you can see that here. Plug in a 4, plug in a 5, and that's the last one we plug in. So this is inclusive. A 1 will be plugged in, a 5 will be plugged in, but this is the first one, that's the last one. And then we add them together. That's what the sigma is saying. Add them all together. So in this case, we add them all up and we get 30. Okay, so I hope you can see that while this notation at first may look a little intimidating, the actual calculation is not necessarily a big deal. Okay, let's look at a few more examples. Okay, let's try these. Okay, in this first example, the first thing we're going to be plugging in is a 1. So let's try it. So what I'm going to have is 1 plus 1 squared. Okay, plugged in a 1, then I need to plug in a 2, 3, 4, 5, 6. So 1 plus 2 squared plus 1 plus 3 squared. Okay, we're going to keep going. And plus 1 plus 4 squared plus 1 plus 5 squared plus 1 plus 6 squared. And then we just add those all together. Now what I like to do is go on the line below and kind of do a little mental math, like 1 plus 1 squared is 2. See, 2 squared is 4 plus 1 is 5. Oh, I've got my squared in the wrong spot on this one. Sorry about that mistake, y'all. 3 squared is 9 plus 1 is 10. Okay, we have 17 here and 26 there and 37 there. All right, y'all, if the video's going too fast, pause it, okay? You can always watch it again. You can always pause it and get caught up with your writing, okay? And then all we have to do is add those up. So we're going to do 2 plus 5 plus 10 plus 17 plus 26 plus 37, and we get 97 when we do that. Okay, so guys, again, I hope you can see, even though this looks a little intimidating, the calculation is not that big a deal. Okay, let's go to this next one. We're going to start by plugging in a 3. Now, if you feel like you kind of have the concept down, why don't you pause the video and try it on your own, then you'll get some feedback when you hit play. Here we go. So plugging in a 3, I get 3 factorial over 3 plus 4 factorial over 4 plus 5 factorial over 5. Now, did you notice that we used a different variable down here on this one, or a different index? That's totally okay. Okay, there's quite a few, and n is a common one. I, k, and n are the most common ones I know of. I think it could probably be many things, although it needs to be whole numbers that are going in. So, for example, notice that up here, we didn't put in 1, then 1.5, then 2. We're only counting in whole numbers, so we put in a 1, 2, 3, 4, 5, 6. Okay, let's simplify this out. The way I'm going to simplify this out is by remembering that 3 factorial is 2 times 3, and we see that it's over 3. 4 factorial is 2 times 3 times 4, and it's over 4. And 5 factorial is 2 times 3 times 4 times 5, and it's over 5. Now the nice thing about that is I can do this. So I'm going to work with smaller numbers rather than working with larger numbers, and I like that. All right, so now we can simplify. So now what I have left is I have 2. Okay, 2 plus 3 is 6, and 2 times 3 times 4 is 24, so I get 32. So guys, you can see, even though it looks horrible, it's relatively simple calculations that you can do with mental math. Okay, we've got one more, so let's see what we get on this last one. Okay, on this one, it's a little different. We're going to be plugging in a 0. Okay, so 0 cubed minus 20 plus 1 cubed minus 20 plus 2 cubed minus 20 plus 3 cubed minus 20 plus 4 cubed minus 20. Notice they're all in parentheses, okay? Now we can start simplifying these. We can do a lot of these with mental math. I'm actually going to bust out a calculator here on my desk as I'm working, though. Okay, so this first one I can see that's negative 20. This one's 1 minus 20, so that's negative 19. This next one, I believe that's 8 minus 20, so negative 12. Here I have 27 minus 20, so 3 times 3 times 3, 27 minus 20, so I get 7. And then what is 4 cubed? 4 cubed is 64, so I get plus, let's see, 64 minus 20, that's 44. So now we need to add all these up. And it turns out that that all cancels out and we get 0. All that work for a 0. Can you believe it? Yeah, that's all right. That'll happen. Let's look at this from a little bit different approach now. Okay, now we're going to practice going the other direction. So what we just did is we looked at sigma notation. That's what that's called with that big Greek letter sigma. It looks like an E, but it's sigma. Now we're going to work that backward. We're going to go from a list of numbers and work backward and write a sigma to represent that. Okay, now this builds on what we learned in the previous lesson, writing down a sequence. So we're going to identify the patterns. Okay, 3, 6, 9, 12. Pattern is we're adding 3 every time. So what do we expect to see? Okay, I expect to see 3n. Okay, let's double check it. If you plug in a 1, 3 times 1 is 3. Check. If you plug in a 2, 3 times 2 is 6. Check. Okay, so we're good. So once I know that I have my rule correct, I'm going to put down a sigma. Okay, n equals, what do we plug in first? We plug in a 1 to get that. So plug in a 1. How many of these are we going to do? So 1, 2, 3, 4. So I'm going to go up to 4. And there's the sigma notation that represents that series. So this is why mathematicians would use it. If they had a long list of numbers, it actually is more efficient to write this than to write out all the numbers, especially if there's like 100 of them, or say, I don't know, 34 of them, like in this next example. Let's consider this next example now, okay? So the thing that jumps out at me about the patterns is everything here is a fraction, so I'm just going to make that note here. The next thing I see is that the number on top is always increasing by 1 through addition. We're adding 1 every time. So that tells me there's probably going to be something like n. We actually have the same pattern in the denominator. So 3, 4, 5, 6, 7, we're adding 1 every time. So we're going to have an n in that one, or 1n, depending. And the next thing that jumps out at me is we go negative, positive, negative, positive. This thing is alternating. So negative 1 to the n is how we did that. I want to test these. I wanted to go through all my drafts before I put the sigma on there, and that'll make it a little bit easier. Okay, let's see. If I plug in a 1 right here, I get a 1. If I plug in a 2, I get a 2. Excellent, that's good. If I plug in a 1 right here, I get a 1. That's a problem. If I plug in a 2, I get a 2. So I'm getting a 1 and a 2. That's a problem. They're too small. But if I added 2 to each of them, 2 plus 2 would match 4, and 1 plus 2 would match 3. So I'm going to put a little plus 2 on there. Now let's check to see if my index on my alternating part of this is correct. If I plug a 1 into here, I have negative 1 to the 1, and that's negative. Check. If I plug a 2 into here, negative 1 quantity squared is positive. Check. So now that I know that this notation is correct, I'm going to put a little sigma on there. What did I plug in first? I plugged in a 1, so I'm going to put 1. Now, y'all, you can pick this. That's one way to fix this. Like if this index was off, you could start at 0 if you wanted, but you may have to then make corrections to this other chunk. Okay, so n equals 1. And then here's where it gets kind of fun. We're plugging in a 1. That's the first number we plug in. What is the last number that we're going to plug in for this series? Okay, in our case, it kind of is easy because it goes 1, 2, 3. We can see it goes right to 34. So we're going to have a 34 up here. Okay, there's one other thing I want to point out today. Okay. We've been dealing with finite series. Okay, we've been adding those up a finite number of terms, whether it's 6 terms or 34, whatever it is. Okay, there are some other vocab terms for that. It's called an nth partial sum. You'll see that in your textbook, and so that will come up. Okay. Now, I want you to also be aware that we can have an infinite series, and that doesn't necessarily mean that they add up to be something infinite. An infinite series rather means we're going to be adding up infinitely many numbers. Now, at first glance, that seems like, wait, that's guaranteed to be infinite. I mean, if you add up infinitely many numbers, you just keep adding, the number is going to keep getting bigger. Well, that's true. It does keep getting bigger, but that does not mean the answer will be infinite. Okay? In this example, 1 plus 2 plus 3 and so on and so on and so on, yes, that would be an infinite. The answer to this infinite series is infinite, or we might say that it's divergent, okay? But in our next video, we're going to see how sometimes when you have an infinite series, you actually can have a finite answer. Okay, that's going to be all for today. Hope you enjoyed the video, and we'll see you next time.